In this podcast, we're going to talk about colligative properties. This is a property of a solution that is affected only by the concentration of particles in solution, not by the nature of the solute. Now that can be pretty confusing, so I've come up with this diagram to help you out. Imagine I have two solutions here. They have the same amount of solute and the same amount of solvent, but they're different solutes in solution. But it doesn't matter in a colligative property. It will affect it the same. It doesn't matter what kind of solute particles are in solution, it just matters how many solute particles are in solution. There are three situations that we're going to discuss in here that are affected by concentration only. The first one is vapor pressure. If we look at these two situations, you'll see the one on the left is a pure solvent. There is no solute dissolved in it whatsoever. On the right, it has a solute dissolved. Well, in order for something to increase vapor pressure, it has to turn into a vapor. And vapor can only be accomplished at the surface of the liquid. On the one on the left, every single one of those particles is able to turn into a vapor. On the one on the right, not as many particles of the solvent are able to turn into vapor. So that would lead to less vapor, which would lead to less vapor pressure. Now how does this occur? Well, imagine that solute inside there has some sort of attraction for the solvent. Because of that attraction, the solvent is much less likely to turn into a vapor and escape the solution. So that leads to a lower vapor pressure. So that leads to something called vapor pressure depression. The more concentrated the solution, the less likely the solvent is to turn into vapor, which leads to a lower vapor pressure of that solvent. The second type of colligative property is boiling point. Imagine I put some water on top of that Torricelli barometer. Now that water will turn into vapor a little bit at a time, and when it does, it'll push that mercury down because the vapor pressure will push the mercury down the tube. Now if I heat up that water, it vaporizes more, which pushes the mercury down even further into the tube. Well, a boiling point is when the amount of vapor pressure of the water above the mercury pushes it down all the way to the bottom, because at that point the vapor pressure is exactly the same as the atmospheric pressure. That's what we call the boiling point. Now if we were at higher altitudes where the mercury level would not be as high in the tube because the pressure on top of a mountain is not as high as it is at sea level, we wouldn't have to push that mercury down as far as we would, say, at sea level. So that's why the boiling point on top of a mountain is not as high as the boiling point at sea level. Now imagine the situation if we didn't have pure water up on top of the mercury column, we had a solution of water and some other solute. Well, the solute, as you remember, does not allow the water to vaporize as much. So we would have to increase the temperature of that solution more than if it was a pure solvent. We have to get the molecules moving faster to vaporize in a solution than we do a pure solvent. So the more concentrated the solution, the higher the boiling point. Pure water boils at 100 degrees Celsius. The more salt we put in that water, the more we have to elevate that temperature in order to get the water to vaporize. The last colligative property we're going to talk about is freezing point, the temperature where a solid is turned into a liquid. If you look at this graph here, you'll see that we've lowered the vapor pressure with the pink bars compared to the pure solvent, which is represented by the blue bars. If you look at the freezing point of pure water, it's at 0 degrees Celsius. Well, if we lower the vapor pressure, look what happens to the freezing point. It's much further to the left, which means that it will freeze much lower. If you look at the boiling point there on the right, the pure substance will boil at 100 degrees Celsius and the solution of water will boil at much higher temperatures. So how does this occur? Well, in order to freeze a substance, you need to have their intermolecular forces increased, and they will eventually form crystalline solids. Well, if we have a solute dissolved in the solution, the solvent has a hard time coming together and making a crystal. We need to slow down the particles even more for them to become a crystal. hence the reason why the freezing point gets lowered. So remember that freezing point depression happens because the more concentrated the solution, the lower the freezing point is going to be. In order to deal with quantitative problems dealing with freezing point depressions, boiling point elevations, and vapor pressure, there's a formula that was developed experimentally. Delta TF equals I KF M. There are 4 variables in here that you need to keep in mind. The change in the freezing point, remember that the delta sign always means change. I, which is the moles of particles that dissociate. Kf, which is the freezing point constant specific for each solvent and is experimentally determined. This value can be found all over the internet. And M, which represents molality. Remember that molality is independent of temperature, so it's a perfect unit to use for concentration. As you can see quickly in this equation, that as molality increases, so will the delta TF. So the higher the concentration, the more the freezing point is affected. Here's a typical problem. In order to help melt ice and snow from the roads in the winter, salt, either sodium chloride or magnesium chloride, is placed on the roads. This lowers the freezing point of the water and allows it to melt at lower temperatures than normal. If one placed a 4 molal solution of each salt, which would cause a more significant impact, the freezing point constant for water is approximately 2.0 degrees Celsius per molal. So I've given you the equation up at the top right. Keep that in mind as we go through this. For sodium chloride, to figure out the change in the freezing point, notice our I is 2. That's because sodium chloride will dissociate into sodium ions and chloride ions, or 2 moles of ions. The Kf for water is 2.0 degrees Celsius per molal, and the molality was 4.0 molal. So if we multiply those 3 numbers together, we get a change in the freezing point of 16 degrees Celsius. Remember that water normally freezes at 0 degrees Celsius. So if we had a 4 molal solution of sodium chloride dissolved in water, it now would not freeze until it got below negative 16 degrees Celsius. For the magnesium chloride, you'll notice that everything's the same except our I, because magnesium chloride would dissociate into 1 magnesium ion and 2 chloride ions, or 3 moles of ions per mole of magnesium chloride. If we take 3 times 2 times 4, we end up getting 24 degrees Celsius. So if we had a 4.0 molal solution of magnesium chloride, that solution would not freeze until it got to negative 24 degrees Celsius. So you can see that magnesium chloride is a much better salt to lower the freezing point of water than sodium chloride. Of course, cities don't use magnesium chloride as much as sodium chloride because sodium chloride is much cheaper to use and also is less corrosive on the metal underneath cars. Here's a quick way to see how colligative properties deal with freezing points and boiling points. The top is of a pure solvent. Notice where the freezing point and boiling point are on the pure solvent at the top. And as we get more and more concentrated, the liquid phase becomes larger. That's because the freezing point gets lowered and the boiling point gets elevated the more concentrated the solution becomes.